Okay. So I hope you got the Excel sheet, right? And also sample PPT. I thought of how do you control all of you to be on the same page. So that's why I created this sample so that you can actually, it's all uniform, right? So it's easy to manage. Otherwise, it's a difficult thing. Second thing is that, so I think 12th September is a deadline for submission of the PowerPoint. So here, actually, you need to look at the literature really well, in whatever area. If you want to ask anything, if you want to discuss anything, you can just ping me on WhatsApp or whatever, right? And I should be able to help you. Uh, and of course, by the way, for the time being, I am in the different office 2212 rather than 2209, right? So I hope you will be able to find. Okay. And now, actually, I need to open this. Okay. So there are a couple of things in terms of codec. Some more mathematics is required, but I think uh, from the last year, what I changed a little bit, I am not talking about constraint codes right now. So, but you will see that in lecture 8, I talked about it, but that's okay, because that subject is quite vast. But anyway, uh, so now I'm going to describe you demonstration by Microsoft. So they wrote Hello World. They designed a system for DNA storage, which is something around. So I mean, it took them to write 24 hours to read and write hello the system. Okay, so you will see that. So I'm going to describe the codec, which is very simple. Okay, and but you will see how they have done it. Okay, so first I'm going to describe that. So as you know, first of all, as I mentioned, there are two important things. One is net information density. Okay, when we want to store data into DNA, we want to make sure that what is the size. So normally, if we don't have any error correction, so we know that when we want to convert bits to ACGT, two bits are required, right? 00011011 will convert it to map to ACGT, right? It's a very, very basic thing. But with when you add error correction, this is going to reduce. And then you want a scheme which is close to 2 as possible with error correction capabilities. So people have designed a different net density like 1.89, 1.99, all kind of things, right? With different codecs. So if people who are going to look at the codec work, they should actually compare all these codecs with respect to this in net information density, right? How do you compute it? Number of input information bits divided by number of bases in the resulting DNA string, right? So you can get this information. There is another density, which is the physical density, and that comes from the architecture of the strand in which you are storing the data, right? So that can give you the physical density, how much physically information you can store. And as you know, that 1 gram of DNA can store 455 exabytes of information. Okay, and there is a scheme which I'm going to talk about, yin yang, which can store up to 432 exabytes of data in 1 gram of DNA, physically demonstrated by George Church. Okay, so these two densities are important. You need to keep in mind. So if you look at here, uh, so after this Church and Goldman paper, there was a Robert Grass in Switzerland. They have done interesting work. And you can see that the information density here, so initial work was 0.83, 0.33, which was very low, right? And then after that, it goes to 1.14, 1.58. So finally, I'm going to describe this paper here actually, okay, which is with the group of Microsoft. So they but it's kind of demonstration, much more thing. And there are many interesting things with Takashi and all these people. This is a very interesting paper in 2017, which is based on fountain codes. So you can see that different variations are there in terms of information density, right? Each of these codecs, each of these codecs you should know. I will be talking about few basic ones, okay, how they work, okay. So people who are looking at the codec, and I think every day there is something new is coming up. I think 2-3 days back there was one paper which is based on convolutional codes. It's a beautiful paper, and then they are using magnetic bits and the combination of DNA and so on. It's a really interesting paper actually. So you will find every day new things are coming. So you need to keep an eye as well. Okay, that's why I said that if you make a resource page, it will be useful for everyone anyway. So there are more papers. These are the initial ones, after 2012. I'm just listing some of them up till 2019. And if you compare these schemes, so you can actually, so people who are writing about the codec, they can also compare something like this: year, published, right? Whether there is, full recovery or not. Whether what is the method of robustness? Whether they use repetition or none of them, or for example, Reed-Solomon RS is Reed-Solomon code. I'm going to talk about it actually. Reed-Solomon code, content code, drawing, having. Okay, so all these things I'm going to talk about, and whether it is error detection or error correction, right? All kind of things, what are the things involved in the codec. So you can summarize something like this, right? Nice report. Actually, you can see that a sample. By the way, this is I have taken this table from Eva. So she has written a bachelor thesis, BTech, 2019, at TU Delft, and you can see that how she has summarizes all the codec. So something like that, if you can write the report when you are doing the comparison, right? So maybe if those people who are doing review for the codec, they can take year-wise division, right? Okay, from maybe certain year to certain year. Some people are doing certain year to certain year. Some people are doing, or also in terms of concept-wise, right? So maybe one kind of codec, one group can summarize, another kind of codec, another group can summarize, right? All that we can, when we discuss, when you start reading, then only we will be able to finalize that. Okay. So these are some of the initial papers. Uh, uh, so I'm going to talk about the first paper, by Akashi, demonstration of end-to-end automation of DNA data storage. A paper published in Scientific Reports in 2019. Okay. This is the important paper by DNA fountain codes, which I'm going to describe actually in details. Okay. And yeah, so some of interesting things are there anyway. So this is the paper, demonstration of end-to-end automation of DNA data storage. Okay. Dennis Test is at Microsoft. So this is the work that they have done with the help of Microsoft. So this is the $10,000 prototype that they developed. You can see that this complete setup is a machine for storing data into DNA and retrieving it. Okay, it's a complete thing. So for sequencing is also there, and synthesizing is also there. With this, all these bottles are there. You can see that. So they stored hello. They converted into bits, and that yields approximately 1 milligram of DNA. Okay, and write and read took 21 hours. Okay, this is the thing. So I'm going to describe the codec for this, what they have used. Very simple, fairly simple codec they used. Okay, so 2019, this is how many years back? 4 or 5 years back, right? So very recent, you see. That was but within 5 years, there are so many codecs have come up. This is very starting thing, right? So you can see how fast the field is growing. Okay, so they have used Hamming codes. So you know about the Hamming codes, especially over the binary or the Curie field, right? They've used a different, slightly different version over Z4, ring of integer modulo 4. Okay, they have used the following code, 3126 code over Z4. So what they did, they constructed a 26 cross 31 generator matrix D by taking I26 5 minus A. You remember this is standard generator matrix form, right? And where, then actually G you can determine from H, right? And H is something like A, and then the bottom portion is I5. A is this matrix. Okay, so this is the codec that they've used. Okay. So how the hello is converted? So hello, you have the ST value, and then ST values are converted into base 4. Okay, so base 4. So this results. So hello will result in this kind of. So total size is 20. Quarts means over Z4, right? So these are 20 length. String has been obtained from hello. Hello is converted into something like this. Then again take it from the thesis. So then they use, I don't know how many of you know about secure hash algorithm, SHA. You have done course on cryptography? Not yet? Okay, so that's a good thing. You can see what is SHA. Okay, secure hash algorithm. SHA 256. By the way, if you have not done this, you can look at SHA lecture on YouTube, on my channel. It is available. You can look at it, right? So they use CRC that consisting of SHA 256. So this is the cryptographic hash function. So basically on that M, which is of 20 quads, okay, you get H is hash function is 110213. Okay, and then applying that hash function, you just concatenate it to M, you get this A. So this is a total length is 26 quads. Okay, so 20 quads are mapped into 26 by adding a hash function. So you just compute the hash function of the whole input and concatenate it at the end, right? You get A. Now, from that H, you can get G. Okay, I think it's a good exercise for you to just do these calculations. Okay, by yourself. Then take that G, multiply with A, you get B. This is our encoding. Okay, remember how encoding is done from the generator matrix? Bits are there, you multiply with G, then you get this. So then you get 31 quads in total. So now you can see that the code was what? 26 quads are mapping to 31 quads. Okay, that was the code actually. Okay, and then a parity check quad P is added. The initial thing. So here actually because it is modulo 4, so you just parity check means what? Just sum it and reduce it to modulo 4 and append that quad at the beginning, right? So this is turns out to be 3. The parity quad is 3 here. So the final code word is this of 32 quads. This is how you do very basic thing. Hello is converted into ASCII values. That is converted into quaternary values. Okay, 0, 1, 2, 3. So I want you to verify what is the mapping, how they convert my bits to quaternary things, right? I leave at an exercise. I may ask again. I'm saying that exam is near, right? So you need to work out. Okay, just verify the calculation. Okay, all the calculations. Okay, then finally once you got this C, they have used very simple map. 0, 1, 2, 3 map to ACGT. So you can clearly see it's not very clever map because there is a repetition of CCC, right? You don't want those kind of things. But they wanted to just demonstrate for a small thing, and it worked actually for the hello thing, right? Okay, so that is a thing. Actually, normally in some sequencing and this thing synthesizers, 3 bits are okay, kind of thing. 3 repetitions are okay. Okay, so you can do the experiment. Okay, it is better ideal thing mathematically if nothing will happen, but it works. Okay, so that is the thing. Trick. Got it? Any question at this? Encoding for Hamming code over Z4. First, you take the parity check matrix. From parity check matrix, you construct the generator matrix. From generator matrix, which is over Z4, right? Then you take the message, convert it into. If I give you a different message, say DAIICT, and ask you to convert it using this process, that's the best thing you can do, right? Take the ASCII values and do all the calculations, you will see what is going to be, what you're doing. Or if you are a very good programmer, you can write a program. Any Python script. By the way, I think Python script is available probably for this. Anyway, you just take the message and get this thing, right? So this is the final ACDT string that is as an output. And then there are cases, when there are no errors, everything else works in the similar manner, right? Encoding, decoding, and there is one error, two errors, and like that you can. Okay. The question that I asked, I'm going to ask you here, what is the distance here? That is you need to work out. What is the distance of that code? Some calculations you need to do. Okay. Because you know that error correction depends on the distance, right? What is the distance, right? If distance is d, you can correct d minus 1 by 2 errors. That is the normal thing for fields. But anyway. Okay, so that was one part about the demonstration of Microsoft for Hello. Hello converted into that $10,000 machine there, and it's coded just few years back. So you can see that plenty of things are there. If you can develop, I think in the whole class, only probably these are the people who are the real ones, but the rest I don't know. So you can do something good easily because there's a lot of low hanging fruit, right? You develop one new codec and you become noticed, right? You can do a lot of things. In fact, yesterday in the meeting, I was asking, we have a lot of people who want to do good work, and I think there's a group at Israel. They are also, by the way, they also started a course on DNA storage this summer. Now they are the second one, but many people are not. So they are but advanced students, but they are also doing projects. So, there is a possibility of collaboration if you are doing something good, okay? Anyway, so now I'm going to talk about Reed-Solomon code. Reed-Solomon code is very, very popular in storage industry, right? From your hard disk to a lot of other devices, right? Reed-Solomon code is used. And a variation of Reed-Solomon code is used. There is a nice book, if you want, you can actually read this book by Bhargav. Is there or not? Okay, so it will come. So before that, I think we need to, let me see if I have it picture here. No. Yeah. I can show you the picture of this book. By the way, this is the paper. This is a paper. Polynomial codes over certain finite fields. It's a beautiful work. And I would encourage you to look at this because the idea is very simple. What they said, take the message bits, M0, M1, M2, Mk minus 1, there are k bits, convert them into a polynomial, M0 plus M1 times x plus M2 times x square and so on, you get a polynomial. The message bits converts into a message polynomial, okay? And that polynomial of degree, of course, not exceeding k minus 1, right? Because basically k. Now, take this polynomial, evaluate this polynomial at the points of the finite field having q number of elements. So like 0, 1, alpha, alpha square, all those things, you just evaluate it and then you form the encoding like that, coding. I'll show you that in details, okay? So this, but I would suggest you can look at this paper, or I think you can look at this book also. Created by Vijay Bhargav and Stephen Becker. Reed-Solomon codes and their applications. Actually, if you really want to look at the storage thing, if you really want to understand the storage business, this code or a couple of variations are given in this book actually. including the first paper, which was about polynomials over certain finite field, right? I mean, polynomial evolution, that original paper. So originally the Reed-Solomon code was constructed in this manner, but then later on people found a much more efficient method, which is using generator polynomial. So we'll talk about it after some time. Okay, this is a important book. So now, in order to understand Reed-Solomon code, I need to recall some of the facts of finite field. I think might have some exposure of finite fields in your discrete path course if you have done it with me, right? Those construction of field with 4 number of elements, 0, 1, alpha, alpha square, if you remember, where alpha is the root of the ground irreducible polynomial, right? X square plus x plus 1 equal to 0 over Z2. If any of you remember anything, okay. Then we made 2 tables with respect to addition and multiplication and all that thing, right? Finite field is a beautiful thing, right? You can do wonders there. Okay. So there, this is the field with Q number of elements, if you remember. In general, if you have an integer modulo P, you know the integer modulo P is a field if P is a prime number, right? And if you take a polynomial over integer modulo P, which is irreducible over ZP, which has no root over ZP, suppose this root is alpha, which is outside ZP, right? Then you attach that alpha over ZP to get field with Q number of elements. So 0, 1, alpha, 2, alpha 3 up to alpha Q minus 2, right? There are Q elements. Q is a prime power. You know that field exists only if, so number of elements in the field is Q, then Q has to be a prime power because you're building it from ZP. ZP gives you field with P square elements. P square will give you P cube. P cube will give you P is power 4 and so on. This is the tower of finite field if you remember. Okay. So now there are certain definitions. So suppose beta is a non-zero element in field with Q number of elements. So I'm taking any element of these 0, 1, alpha 2, alpha Q minus 2. So basically you can also write down all these elements of alpha 2 alpha, and alpha Q minus 2 also as a power of alpha, if you remember. Because in the case of GF4, it is 0, 1, alpha, alpha square, right? Alpha cube turns out to be 1, if you remember, right? Those things were there, right? So order of beta. So if beta is any non-zero element from this finite field, order of beta is defined as smallest positive integer m such that beta raised to power m is equal to, beta raised to power m means beta 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 m times gives you 1, right? The smallest positive integer m. So now as an example, if I take Z5, so this is also a field with 5 number of elements 0, 1, 2, 3, 4. So 1 raised to power 1 is 1, order of 1 is 1. 2 square is 4, modulo 5, which is 4 itself. Cube is 3, modulo 5. 2 raised to power 4 is 1, modulo 5. 5 into 3 is 15, right? So essentially order of 2 is 4. This is the order. I am giving you an example, right? Order of an element of a finite field is the smallest positive integer m such that beta raised to power m is equal to 1. So now we can clearly see that order of 3 is equal to 4, order of 4 is equal to 2. So there are 2 elements, 2 and 3, which have all the 4 elements. So basically if you take 2, you are getting all the 4 elements. Non-zero I am talking about, right? So you are getting 4, 1, 3, right? And of course 2 raised to power 1 is 1. 2 raised to power 1 is anyway 2, right? So all the 4 elements you are getting here. So this is kind of primitive element. So the 2 is known as primitive element, which generates whole thing. I think if you have done a course on group theory, probably you know that there is a generator for the group, right? Cyclic group, right? Those kind of things. Basically, if you take the non-zero elements, they form a multiplicative group, right? So there will be generators. So basically here, 2 and 3 are known as primitive elements because their order is order of the whole field. Non-zero elements, basically, because total field has Q elements, and if you delete 0, you will be Q. It will be Q minus 1 element. So in this example, 2 and 3 are elements of order Q minus 1, right? which is 4 here. So 2 and 3 are kind of generators. They are known as primitive element. Any question at this point? ये सब किया होगा वैसे शायद पहले, राइट? इसकी मैंने किया, कुछ याद आ रहा? Just recalling, huh? 2 and 3 are primitive elements. Okay, great. And if I ask this question, how many elements are there in field with q number of elements of order t? Answer is, a beautiful answer is phi of t. You know what is phi of t? Euler-Torsion function. Cryptography, in cryptography also you might have seen, huh? Yeah, so Euler-Torsion function is all those elements less than t and with GCD 1 with t, right? How many of them are there, right? It turns out that the number of elements in GFQ of order t is phi of t. For example, I mean this function phi of 10 is what? 4. Why? Because 10 is 2 into 5. Since 2 and 5 are prime numbers and phi is a multiplicatory function, so phi of 10 is equal to phi of 2 into 5 is equal to phi of 2 into phi of 5. Now, if p is a prime number, phi of p is equal to p minus 1. So phi of 2 is what? 1 and phi of 1 is, sorry, phi of 5 is 4. So phi of 10 is 4 actually, right? Okay. In general, this is function phi of t is of t times partial product p divides t 1 minus 1 by p, where p is a prime. This is also a formula to compute this. You can see that phi of 6 is how much? 2, because phi of 6 is phi of 2 into 3, which is phi of 2 into phi of 3. Phi of 2 is 1 and phi of 3 is 2. So overall thing is 2. Phi of 15 is 8. So there are 8 elements less than 15 and with GCD 1 with 15, right? You can see that's the definition of Euler-Torsion function. The number of elements of order t in GFQ is phi of t. Beautiful result, right? Now, if I ask, so you just saw that integral model of 5, that field, there are 2 primitive elements, 2 and 3. If you ask this question in general, how many primitive elements are there in GFQ? So the answer is phi of q minus 1. Okay. That's also interesting thing. You can check that in case of q is equal to 5, phi of 5 minus 1 is phi of 4. Phi of 4 is how much? Phi of 4 means how many elements are there less than 4 with GCD 1? With 4. Only 2, right? So basically, there are 2 in that case, okay? Okay, now as an example, if you take field with 16 number of elements, and you can see that elements are 0, 1, alpha, alpha square up to alpha raised to 14, and the polynomial that we are taking is phi of x is equal to 1 plus x raised to 4. It is of degree 4 over z2. This polynomial has no roots over z2, right? Correct? It has no root. And since it is degree 4, it will give you a field with 2 raised to power 4 number of elements, which is 16 elements. And because of this, I mean, so alpha is a, what is alpha? Alpha is the root of this equation. So alpha raised to power 4 plus alpha plus 1 is equal to 0. That means alpha raised to power 4 is equal to minus alpha plus 1, which is alpha raised to 4 is equal to alpha plus 1. So in that manner, you can compute all the powers of alpha. Alpha raised to power 5, alpha raised to power 6, and so on and so forth, up to alpha raised to power 14. And then alpha raised to power 15 turns out to be 1. Okay, just like that. Alpha raised to power cube is 1, right? Here alpha raised to power 15 is 1. Now, alpha, so out of these elements, how many of them are primitive elements? You can check. I think I would ask you to do this verification that alpha, alpha square, and alpha raised to power 4 are the primitive elements. Means order of alpha square, and order of alpha raised to power 4 is q minus 1. What is Q here? 16. So all these elements have order 15. Got it? So I want you to verify this, that the order is, so that these are the primitive elements. So order you can compute. How will you compute order? Alpha, alpha square, alpha cube, keep on multiplying until you get 1, right? So you can keep on doing this. So the smallest positive integer, so order of beta is smallest positive integer m such that beta is for m is equal to 1, right? So you can compute the order of each of these elements. And you can also compute the order of alpha raised power 3 and alpha raised power 5. You see that these are not primitive elements. By the way, there is another interesting relationship. As you know, from reals to complex, when we go, in real case, if there is a equation like, x square plus x plus 1 is equal to 0 over reals, what are the roots? Complex numbers, right? You can find out minus 1, so minus b plus 1 is square root of b square minus 4ac divided by 2a, right? That formula you can compute. You can see that, so either roots of a quadratic equations are reals, which is okay. But if there is one complex root, complex pair will also appear. If x plus iy is a root, x minus iy is also a root, right? Complex pair also occurs in the roots in the quadratic equation. Here, similar thing happens here. So actually, alpha square is kind of conjugate of alpha. Alpha is for 4. So these are all conjugates. You can, similar kind of relationship exists here also. Things are much more beautiful, I would say, in terms of mathematics. Okay. It's all connected, right? So, I think if you want to compare with the field with 4 number of elements, you can probably see it much better. So what are the primitive elements in field with 4 number of elements? Alpha is obviously their primitive element, right? Because it gives you everything. 0, 1, alpha square is a field with 4 number of elements, right? So how many primitive elements are there? I can ask similar questions anywhere, right? How many primitive elements are there, right? So, and of course, phi of q minus 1. So basically, if q is 4, 4 minus 1 is 3, phi of 3 is how much? 2. So there are 2 primitive elements with field with 4 number of elements. What are those primitive elements? Alpha and alpha square. So alpha square is conjugate of alpha. Just like that, if there is a complex number, there is a complex conjugate is also root. In a similar manner, alpha and alpha square are conjugate to each other. And this looks good because alpha into alpha square is what? Alpha cube, which is 1 in field with 4 number of elements, right? Okay. So it's a nicely, I'm not writing anything, I'm telling you because I'm just recalling, right? So I hope you'll be able to understand, right? But as a matter of fact, I mean, like you can do a practice, just compute these things and that will be enough for you to, recall everything. Now, there is another definition known as PP, primitive polynomial. Okay. So primitive polynomial is a polynomial having primitive elements as its root. Okay. ऐसा polynomial जिसके roots primitive elements हो उसको primitive polynomial बोलते हैं, right? And primitive polynomials are very, very important. So let me show you. How do we find this? How do we find these primitive polynomials? So this theory actually. So what I need to do for each prime actually. So depending upon what we are looking at. So suppose we are looking at field with 16 number of elements. Then I am looking at modulo 15. Okay. So let me show you what we are doing. So if you take integer modulo p raised power m minus 1, it is a ring, obviously, right? Having how many elements? P raised power m minus 1, where p is a prime number, m is a positive integer, right? So now, basically, we form what is known as cyclotomic coset. Cyclotomic is a word which means circle cutting. Okay, it's a beautiful thing. Circle cutting. Okay, so what you do? Cyclotomic coset, CS means cyclotomic coset containing the element S. This is, you start with S and for some prime P. So then you multiply P into S, then P square into S, P cube into S. Keep on doing this until you get back the original thing. So for example, here you keep on multiplying. So then we are reaching up to P raised power ms minus 1 times S, where ms is the smallest positive integer such that P raised power ms into S is equal to S. You are going back here. Modulo P raised power m minus 1. That is the whole scenario. Okay. So let us take an example. I hope you will understand this. This is known as cyclotomic coset. Okay. So let us take this example. P is equal to 2. Okay. And so m is equal to 4 here. So basically we are looking at modulo 15. See, if P is equal to 2 means what? This is 2, m is 2, sorry, m is 4, 2 raised power 4 minus 1 is 15. So this is 15. We are looking at modulo 15, everything, right? And we are going to generate the cyclotomic cosets. So first, because you see in this ring, modulo 15, right? 0, 1, 2, 3, up to 15, all elements will be there, right? I mean, modulo 15, 0 is there, right? So what we do, we basically start with 0. C0 is what? 0, because C, if you multiply with 2, P is about 2 here. You will get 0 only, no extension. The first is C0, very good. So now I have to make the second cyclotomic coset. And how do I do that? So 0 here has been taken care of. What is the next number there in modulo 15? 1. So I take 1. So take C1. Now you multiply with 1 with 2, you get 2. Again multiply with 2, you get 4. Again multiply with 2, you get 8. Everything is modulo 15. You need to keep in mind that 8 you multiply with 2, modulo 15 is 1. You are back. Right? This is cyclotomic coset containing 1. Okay? Then 0 has been taken care of. 1, 2, 4, 8 has been taken care of. What is the next number which is missing? 3. Right? So start with 3. 3. So 3 is the first element. 3 into 2 is 6. 6 into 2 is 12. 12 into 2 is 24. Modulo 15 is 9. 9 into 2 is 18. And modulo 15 is 3. We are back with this, right? Now what? So which number I should take now? 0 has been taken care of. 1, 2, 4, 8, 3, 6, 12, 9. So obviously 5 is missing, right? So 5 we need to start. Okay, start with C5. 5 is 5. 5 into 2 is 10. 10 into 2 is 20. Modulo 15 is 5 back. So this is also done. Next, so which number is left? 7, right? Start with 7. C7 is equal to 7. 7 into 2 is 14. 14 into 2 is 28. Modulo 15 is 13. 13 into 2 is 26, right? Modulo 15 is how much? 11. And 11 into 2 is 22. Modulo. So I hope you, whatever. So you are able to do this, right? So now you see, do we need to go further? So all the elements of modulo 15 are here, right? Everything is partitioned. So these are known as circle cutting, means cyclotomic cosets. And they are beautiful thing, and they will help you to find out the primitive polynomials. Okay, and how do we do that? As an example, what I'm going to just give you some hints. Maybe next time we can discuss more, but I'll just tell you. Alpha we know, right? So take x minus alpha raised to power 1. Take this as a power of alpha. X minus alpha raised to power 1 into x minus alpha square into x minus alpha raised to power 4 into x minus alpha raised to power 8 and multiply and expand, keeping that polynomial x raised to power 4 plus x plus 1 is equal to 0. That means alpha raised to power 4 plus alpha plus 1 is equal to 0. You simplify, you get one polynomial. Okay. It's a beautiful trick people have discovered, right, to find out these polynomials, right? Similarly, you can do the other one. I mean, you can actually do this one, this one, this one. It turns out that actually you will get the factorization of the polynomial x raised to power p minus 1 minus 1, right? So whole factorization in terms of these polynomials can be obtained. It's a beautiful trick. And that's why, because these are all roots of basically what we are doing. X raised to power p raised to power m, right? That equation we want to factorize it completely. So this factorization can be done by this cyclotomic process. This trick is really beautiful, right? I would suggest you can try this as an example. Say for p, take p is equal to 2 only, but modulo you can take. So this is I have done it for field with 16 number of elements. You can do it for field with 4 number of elements, right? Same thing. You can see what are the cyclo. I have taken a non-trivial example. You can take the easy one to at least to do this, right? For what modulo we need to take for field with 4 number of elements? Here I have taken modulo 15 because we had 16 number of elements. See, you look at this. When we wanted to construct 16, so P is 2, M is 4, right? So when P is 2, M is 2, 4 minus 1, 3. So you need to do only modulo 3, right? So you need to do modulo 3 business and partition everything. So, I mean, because that is very trivial case, that's why I have not taken it, but you will see that everything is clearly sitting well there, right? Are you getting me? No. How to determine just by looking at this, see, because here, when we wanted to do it for 16, I took it modulo 15, just decrease 1, right? And so modulo 15, and we do the all calculation, keeping the mind p is equal to 2 there. So in the case, when we want to do it for we field with 4 number of elements, right? That is GF 2 square. So P is 2, M is 2. 2 square minus 1 is what? 3. You have to do it modulo 3 and you can do the calculation. I think some of you might have obtained, right? Are you able to find out for modulo 3? You can just do it actually. I think you have 2-3 minutes, you can just do it. So 2 cosets will come. How many cosets? Cyclotomic cosets will come. One, you have to start with 0. So C0 is equal to 0. Next, C1, 1 and 1 into 2. And 2 into 2 is what? 4. Modulo 3 is 1. So 1, 4. And then anything else? All exhausted. So now you see the beauty. So now the cyclotomic coset, one is C0, other one is C1, which is 1, 2. So the polynomial is x minus alpha raised to power 1 times x minus alpha raised to power 2. So x minus alpha into x minus alpha is square. You multiply, you get x square plus x plus 1. The beauty. Right? Are you getting what I'm saying? So the factorization can be done easily, right? X square plus x plus 1 is nothing but x minus alpha into x minus alpha square, right? And that is there just by looking at the cyclotomic quotient, we can factorize, right? I think that's all for today. So in the next class, I hope we will be able to do enough material for your exam, which is on 4th, right? We have to waste two classes for those purposefully, but still you see. It is anyway. Thank you. Yes,